unit, we will look at the properties of disinfectants along with several disinfectants that are commonly used both in water treatment and in wastewater treatment. So let's just look at the properties of disinfectants. And I want to divide this, and we'll talk first about water, and then we'll talk about wastewater. So when you're looking at a disinfectant, what properties do we want for water treatment? What properties do we want for disinfectants?
Could it be that it's like able to be consumed by humans?
Okay, so we want something that is non-toxic. Absolutely. It makes no sense to disinfect with something that is toxic. What else? Most of Europe, or much of Europe, uses ozone and not chlorine. We talked early on about water being palatable and potable. Much of Europe, they don't like the taste of chlorine, so they use ozone. Something that is readily reactive, exactly, okay? It has to react or destroy the pathogens that are present. As I mentioned, cryptosporidium is extremely resistant to chlorine. So if there's crypto in the source water, that's a problem. It has to be able to inactivate or kill the pathogens present. And the reason we use inactivate is because, for instance, viruses are not alive. So it's kind of, kill doesn't make sense. So that's, inactivate is typically the term that's used. So it has to do this over the temperature range of the water. In Flint, while they were treating Flint River water, that temperature of the Flint River water ranged from 2 degrees C to 23. It has to be effective over that range. The pH range. It has to be effective at variable concentration or composition. It's a good question. Other than being more palatable, are there other reasons to use ozone instead of chlorine? Ozone is much more effective at inactivating crypto, viruses, and giardia. It's a much stronger oxidant than chlorine. It doesn't produce dechlorinated disinfection byproducts. It does produce, if there's bromide in water, so we're talking bromide, that bromide can react with ozone to produce bromate, and that is regulated at 10 micrograms per liter. So when we look at the example, you'll see we'll talk about bromide. But major reasons, much stronger oxidant than ozone, much more effective at inactivating cryptoviruses and giardia than is chlorine. Other reasons we might want to, or other properties we would want of a disinfectant. It has to be cost effective. People don't want to pay a lot for water. It has to be safe to transport, store, handle, and apply. So for instance, we'll talk about gaseous chlorine. The East Lansing Meridian Township plant used gaseous chlorine until there was a significant amount of development around that plant, and there was concerns about storing chlorine gas and the impact if there were a leak on the residents in the area. So they switched to liquid chlorine, hypochlorite. We need to be able to determine a residual. So this residual has to be easy to determine and inexpensive. And we will talk about primary disinfection and secondary disinfection. We'll talk with secondary disinfection. Here we're looking at maintaining a residual in the distribution system. So primary disinfection, we're looking at inactivating the organisms, any pathogens. Secondary disinfection, we're looking at maintaining a residual. Now, if we talk about wastewater, what properties would we want for wastewater? Those of you in 480, we did an experiment where we looked at chlorine decay. Why did we care about chlorine decay? Okay, we want to remove bacteria. It's the same thing. We want to kill the bacteria. We want pathogen inactivation. Why did we worry about and why did we design a dechlorination basin? Those of you in 480. Lab 2 was all about the determining the kinetics and designing a dechlorination basin. Why did we design that dechlorination basin? Why didn't we just discharge wastewater with chlorine? We don't want a residual. Why? Because we don't want to kill the natural organisms in a receiving body of water. So the whole purpose of that dechlorination basin was to ensure that there wasn't a residual. What other properties do we want for wastewater? It also needs to be cost effective and it needs to be safe for transport, storage, handling, and application. The last thing is we don't want byproducts that are toxic. We don't want organisms to be in the ecosystem to be adversely affected. So we want to ensure that we are killing these bacteria or inactivating pathogens, but we don't want to adversely affect the ecosystem and the receiving body of water. So this gives you some sense of what we're looking for in terms of properties and how we will make decisions about the disinfectants. So we'll start looking at a number of disinfectants. The first one is chlorine. One of the things I want to make sure, okay, when we're talking about chlorine, we're talking about chlorine gas, aqueous dissolved chlorine gas, hypochlorous acid, and hypochlorite. We are not talking about chloride. Chloride, yes, at very high concentrations, would be a disinfectant. It would kill freshwater or organisms that survive in freshwater. However, to accomplish that, the levels would be so high that that water would not be drinkable. So these are the four species we're talking about when we talk about chlorine. So we can apply it as chlorine gas. You see the gas tanks here. We can apply it as liquid, basically bleach, or calcium hypochlorite, which is a solid tablet. And if those of you have a swimming pool and you add the solid tablets to the pool to disinfect, what you're adding is calcium hypochlorite. This gives you some idea of the application. So in this case, you can see here is our effluent. This is similar to what you'd see in a wastewater plant. And you've got a chlorine mixer and you've got a chlorine contact diffuser, adding the chlorine and a contact chamber. In this case here, again, it's with wastewater. You've got a Venturi injector, and you are injecting right into the pipeline and mixing in this turbulent region here in order to disperse the chlorine gas. Now, if we add chlorine gas to water, so we inject chlorine gas, some of that will dissolve to form aqueous chlorine. That aqueous chlorine reacts with water to form hypochlorous acid. Notice it releases H+, so it's going to lower the pH and chloride. And this reaction is very rapid. It's complete within a few milliseconds. Hypochlorous acid can dissociate, releasing proton, forming hypochlorite, but hypochlorous acid is about 80 to 100 times more effective than hypochlorite for killing E. coli. So that means that our dose is pH dependent. So in order to get the same level of treatment, we're going to need more chlorine added at a higher pH. We talk about free available chlorine, and that is the sum of hypochlorous acid, hypochlorite, and aqueous chlorine. As I mentioned, when we add chlorine gas to water, it reacts or dissolves first to produce aqueous chlorine, and that aqueous chlorine can be hydrolyzed to form hypochlorous acid plus H+, and the hypochlorous acid dissociates to release H+ and form hypochlorite. And this is a speciation diagram showing the concentration of hypochlorous acid and hypochlorite. And we said that hypochlorous acid is about 80 to 100 times more effective than hypochlorite. So you can see at pH values less than the pKa for this dissociation reaction, hypochlorous acid predominates. At pHs above the pKa, so here's the pKa, at pHs above the pKa, hypochlorite predominates. So what does that mean in terms of disinfection? Those of you in 481, I believe you did a problem, something similar to this. Okay, what it means is we're going to have to add a lot more of our chlorine disinfectant at higher pHs than we would at lower pHs in order to achieve the same level of disinfection. And you'll see this later when we look at what we call CT tables. Now we can add chlorine. I wrote the reaction as adding chlorine gas, but we can also add hypochlorite in the form of sodium hypochlorite or calcium hypochlorite. Sodium hypochlorite is typically provided as a liquid. It is bleach. So if you purchase bleach, what you're actually purchasing is sodium hypochlorite. Calcium hypochlorite is typically provided as a solid. So for instance, if you have a swimming pool and you purchase chlorine tablets, what you are typically purchasing is a calcium hypochlorite. So advantages and disadvantages of these different forms. When we look at chlorine gas, it's cheaper than either sodium hypochlorite or calcium hypochlorite, it will tend to decrease the pH. Just saw when we add chlorine gas and it hydrolyzes, it releases H plus and Cl minus. It will consume alkalinity. If you remember, alkalinity is equal to bicarbonate plus 2 times carbonate plus OH minus minus H plus. So if we increase H plus, we lower the alkalinity. The salts, both as sodium and as calcium, are more expensive. On the other hand, they're safer. They're safer because chlorine gas is heavier than air. So if there is a leak, it tends to kind of sit close to the ground surface, which means potential contact with people, less dispersion into the atmosphere. Typically, the salts will contain alkali, and that helps to enhance the alkalinity. Why would we want to enhance the alkalinity? Why do we even care about alkalinity? pH change, exactly. We want to ensure that we don't have significant pH change in either the treatment processes or during distribution. So by enhancing alkalinity, that helps to resist these pH changes. Adding these salts tends to increase the pH, and it also adds total dissolved solids to the water. So just comparing chlorine gas to these salts, this kind of gives you a sense of the advantages and disadvantages of each. As I mentioned, the East Lansing Meridian Township switched a number of years ago from chlorine gas to adding liquid chlorine. Why?
Did they get like more residents in the area or something?
Exactly, because originally the plant was on the outskirts of East Lansing, and then as subdivisions built around it, there was a concern for the safety of that population, so they switched from chlorine gas to sodium hypochlorite. On the other hand, the Williamston water treatment plant, which is in a rural area of Williamston, there isn't a significant number of population surrounding that, uses chlorine gas. So let's do a quick problem here. We often use both the terms chlorine dose and chlorine demand. So when we're looking, for instance, at, and then we also use the term residual chlorine. So if we think about this in terms of, here's our treatment process. This is our disinfection. We add chlorine or hypochlorite at some dosage. We have a distribution system. We want to ensure that we have a chlorine residual in the distribution system. Okay. The World Health Organization recommends that there be at least 0.5 milligrams per liter after 30 minutes of contact. The New Zealand regulations demand, at the point of delivery, actually, it's not really, it should, it's a recommendation, should have an available free chlorine of 0.2 to 1.0 milligrams per liter. Remember, in Christchurch, until very recently, they weren't even required to disinfect. And then in the US, under the surface water treatment rule, 95%, so 95% of the samples have to have at least measurable chlorine residual. And that's for, I don't know, crazy line is for more than two consecutive months. So different regulations for different countries, but in essence, we're talking about the same thing. We're talking about ensuring at some home in the distribution system that we have, in the case of the US, measurable chlorine residual. Some states actually do specify what that chlorine residual, minimum chlorine residual has to be. But from a federal regulation, it is just measurable chlorine residual. So at this point here, according to the specifications we've been given, we have 49.9 kilogram per day of chlorine that we're adding. We're treating 37,850 cubic meters per day. That's 10 million gallons per day. And you're asked to determine the chlorine dosage and the chlorine demand. So our dose is simply the 49.9 kilograms per day, or a million milligrams per kilogram. We divide that by the flow rate, multiply by 1,000 liters per cubic meter, and that is a dose, a dose of 1.32 milligrams per liter. At this point here, which corresponds to 30 minutes of contact in the distribution system or in a storage tank, it's 0.5 milligrams per liter. So that's what we measure here. So that's the residual. And then the demand, chlorine demand is just the difference between those two. So it's 0.77 milligrams per liter. So that illustrates the issue, what we talk about when we talk about dose, residual, and then the demand. Now, in terms of how these react, I'm not going to go into any great detail, but basically both chlorine and hypochlorite react by disrupting the bacterial membrane, disrupting the various enzymatic functions. They also denature the nucleic acid, and by altering the permeability of the cell, which occurs because they've disrupted the bacterial membrane, that results in killing the organism. However, protozoa and many viruses are resistant to chlorine. So if we look at the CT tables, you'll see when we talk about CT, that CT value for crypto is quite large for the chlorine and hypochlorite. Now we also can use chloramines. And for instance, the Lansing water treatment plant, so it's named the John Dye plant, uses chloramines. So these are formed by the reaction of chlorine and ammonia, and that produces monochloramine, dichloramine, and trichloramine. Now these are used because they have a longer lifetime in the water, but that means that it's less reactive. So if it's less reactive, it's less effective at disinfection. It does produce fewer disinfection byproducts, BBPs, than chlorine, but the problem is that there is some concern with nitrosamines, which can be formed by the reaction of chlorine in the presence of ammonia. So if it's less reactive, it's less effective. It's slower acting, takes more time to achieve the same level of disinfection. Because of that, it is not used as a primary disinfectant. Now, what does that mean? We talk about primary and secondary disinfection. Primary disinfection is that disinfection that is used to control the microbial population in the water, that's actually used to inactivate cryptosporidium, inactivate viruses, and kill bacteria. Secondary disinfection is that disinfection that's required to ensure that we have a residual in the distribution system. So when we talk about the CT concept, there we're looking at primary disinfection. The other problem with chloramines, it can change the redox chemistry. It's more reducing environment, and that has been shown to cause problems with the release of lead. So for instance, in Washington, D.C., actually it's now probably close to 2 decades ago, when they switched from chlorine to chloramines, that resulted in a significant increase in the lead concentrations in the treated water at the tap because of the change in the redox chemistry. The other problem is that it can result in bacterial regrowth. You're adding ammonia, and if that ammonia is in excess, then that can result in bacterial regrowth, which can also result in the release of lead. So that's the disadvantage of using chloramines. The major mode of operation is to disrupt enzymatic function. Now, the formation of chloramines depends both on pH and dose. And as you can see here, looking at it as a function of pH, if we are in the pH region of most natural waters, we're in this region here, and for the here, monochloramine will predominate. So in this region here, monochloramine predominates. Temperature and contact time also are important in terms of trihalomethane, in terms of chloramine formation. This diagram here demonstrates what we refer to as breakpoint chlorination. We're going to introduce another term called combined residuals. Combined residual is, we mentioned that free is aqueous chlorine plus HCl, hypochlorous acid, plus OCl minus. So that's when we talk about a free chlorine residual, that's what we're talking about. When we talk about combined chlorine residual, we're now talking about the chloramines. The major of the 3 chloramines, monochloramine is the most effective disinfectant. So what this shows is the chlorine residual as a function of dose. So what you see here, initially, in this region here, what's happening is we have no chlorine residual. So the chlorine that we're dosing is reacting with other species, organic matter, reduced metals. And then we increase the dose. And if we have ammonia present, then we form monochloramine. And as we increase the dose, the combined residual increases. If we continue to increase the dose, now what we start to form is the dichloramine. So we're converting the monochloramine to dichloramine, but dichloramine isn't a strong disinfectant. So now our chlorine residual starts to decrease. At point C, we essentially have consumed all of that ammonia. We convert our dichloramine to trichloramine, but because we've consumed these reactive substances here, we consume all of the ammonia, so we can't form any more chloramine. And now we see that now we start forming free chlorine residual in the form of hypochlorous acid and hypochlorite. So if you think about this as happening sequentially as we continue to increase the chlorine dose. Any questions about this graph here? Another disinfectant that we can use is chlorine dioxide. Chlorine dioxide cannot be stored. It actually must be produced on site. And these are the various reactions that result in the formation of chlorine dioxide. And I'm not going to go into these in any great detail, but this is the disinfectant. So you can see by this reaction also, we're going to increase TDS because we have NaCl. Same thing here. And in this reaction here, we're going to produce a sodium hydroxide. So we will both increase TDS and we will increase. What we're adding is sodium chlorite, and forming chlorine dioxide. So this is the disinfectant. Now the advantages of this are that chlorine dioxide is very soluble. It's a strong disinfectant against both bacteria and viruses. So remember that chlorine itself isn't that effective towards many viruses. It doesn't react with ammonia. It won't form chloramines, and it does provide a residual. The main disadvantage is you're conducting those reactions on site, and if you're not very careful in managing those reactions, you can produce chlorate and chlorite, which are toxic. So you don't want to produce either of those. It denatures proteins in bacteria and viruses more effectively than chlorine. So as you'll see, it's superior to chlorine in terms of its effectiveness on bacteria and viruses. It also inactivates Cryptosporidium and Giardia, but it's not as effective as ozone. Ozone is the next disinfectant we'll talk about. I'm going to go back. Actually, we'll just do this one. So when we look at I've mentioned this a number of times in terms of disinfection byproducts. So we've talked about number of compounds that contain chlorine. So when we're looking at, and this is from chlorine gas, aqueous chlorine, hypochlorite, hypochlorous acid and hypochlorite. All of these result in these disinfection byproducts. Trihalomethanes are carbon with either chlorine or bromine. So it can also be one bromine and two chlorines. It can be two bromines and one chlorine. It can be three bromines. So we can have, this is chloroform, this is dichlorobromoform. Dichlorobromoform. It can also produce haloacetic acids. So this is a haloacetic acid. So it's dichloro here. And we have two carbons. We have a carbon here and a carbon here. And this is our acid function. These are the only two of the disinfection byproducts that are regulated in the United States. Can also form haloketones. This is a haloketone. The X would be typically either a chlorine molecule or a chlorine atom or a bromine. Can form chloral hydrate. And this is the chloral hydrate. So again, we have C2, 3 chlorines, and in this case, we have 2 OH groups. Can form chloropicrin. Chloropicrin is regulated in much of Europe. It is not regulated in the United States. And it's a nitroso compound here with a carbon and 3 chlorines. Can produce haloacetonitriles. And this is a haloacetonitrile. From chlorine dioxide, as I mentioned, the major toxic byproducts that we're concerned about are chlorate and chlorite. And from chloramines, one of the major compounds that we're concerned about are the nitrosamines. So in addition to the chlorine compounds, we can use ozone. Ozone is produced on site by electric discharge. That kind of sweet smell after a thunderstorm, that what you're smelling is ozone. Ozone is widely used in Europe. It's actually the preferred disinfectant in Europe over chlorine. It is extremely effective. It's a powerful oxidant. And it's effective as a bactericide, viricide, and it inactivates oocysts. Unlike chlorine, it does not add a taste. It does not have add any odor to the water. The disadvantage is that it does not produce a residual. It's more expensive than chlorine. And the major disadvantage is the formation of bromate. So you have bromide in water that reacts with ozone to produce bromate. The MCL is 10 micrograms per liter in the US. And typically we use about a 0.1 milligram per liter cutoff for bromide. So if the concentration of bromide in water exceeds 0.1 milligrams per liter, then you want to think about the formation of bromate and either look at mitigation strategies, which are looking at, for instance, changing the pH to change the reaction chemistry in order to reduce the formation of bromate. So in terms of what factors affect efficacy And here we're looking at chemical disinfectant. What I have here is a list of various oxidants. And you see ozone is right here. Hypochlorous acid is down here. Hypochlorite is here. Chlorine dioxide is here. The higher the redox, the potential, the stronger the oxidant. So you can see ozone, if we look at ozone, it's 2.07. If we look at hypochlorous acid, it's 0.95. Ozone is a much stronger oxidant. The strongest oxidant we have is the OH radical. We typically don't use OH radicals as disinfectants because they react with just about everything, and it's very difficult to maintain that disinfection. So the factors that affect efficacy, we've talked about dose, contact time. Another parameter is turbidity. Why would turbidity affect disinfection?
Could the chlorine potentially react with some of the matter?
Exactly. It reacts with the particulates, consumes chlorine, and there's just less disinfectant available to achieve what we're looking for, which is disinfection. Likewise, the presence of reactive species. These can be reduced iron, reduced manganese, anything that would potentially consume, react with ozone. pH, we mentioned HOCl versus OCl minus. The HOCl is about 80 times more effective than OCl minus. So pH will play a significant role there. Temperature also plays an important role. It plays a role in terms of how rapid the reaction is. The biology of the organism, the type of organism, how susceptible is that organism? And even for the same organism, different bacteria will have different susceptibilities. Just like if you kind of think about it, you're living in a house with different roommates. One of them comes down with the flu. You don't all come down with the flu at the same rate. It doesn't affect everybody the same way. Well, it's no different with bacteria, oocysts, etc. And then lastly, the relative strength of the disinfectant. So all these will affect the efficacy of the disinfectant. Now, we also talk about UV radiation. In tutorial, we'll actually have two different lectures, one both from engineers from Black and Veatch, which will talk about design of ultraviolet radiation system. These are becoming more and more common in both in our water and our wastewater treatment systems. It's an effective bactericide. It inactivates viruses. There are no known byproducts formed from the reaction of UV or from the irradiation of water. And as I've mentioned, it's effective bactericide and virucide. Disadvantage, there is no residual. So we still need to think about what are we adding to ensure that we have a residual. The water must be free of turbidity. If you're illuminating water or radiating water, that light must be able to penetrate through the entire water column. And if you have turbidity, it's going to block. Those particles will block the light penetration. You can get slime deposits, especially in wastewater systems, on the lamps. You can get chemicals precipitating on the lamps, and that decreases the transmission of light, so it decreases the efficiency. So you don't want either slime, chemical precipitates depositing on these lamps. A lot of lamps now are what they call self-cleaning to try and ensure that they can maintain the desired transmission level. And then there's a difficulty in determining the dose. With, for instance, with chlorine residual, we can do a chlorine test. Relatively inexpensive to purchase, easy to do, to purchase the test, easy to do. That's much more difficult with UV radiation. The other disadvantage is we need high doses to inactivate cryptosporidium. The way that it works is predominantly to induce mutations. So it affects the DNA, and that inhibits replication. There is some concern with bacteria that the organism can actually repair itself after irradiation and then therefore still be able to proliferate. In terms of factors that affect it, most of these I've really mentioned in terms of talking about it, but wavelength also affects it in terms of the energy, the intensity of the light, condition of the lamps. I talked about not having growth of slime or chemical deposits on the lamp. And then the ability for that light to actually be transmitted through the solution is extremely important. So for instance, turbidity, anything that absorbs UV light would then therefore prevent transmission. And also the presence of particles can shield, or particulates can shield the bacteria from the UV light. And then again, the biology of the target organism plays a significant role.